Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on advanced transition metal organometallic chemistry. We have been talking about transition metal arene complexes, its structure and bonding over the last few lectures. In the past lecture, we had seen in this regard that how the p orbitals of arenes, particularly in benzene, stack up through using this linear combination of each other to form various fragment molecular orbital. So, what we had seen that 6 p orbitals in benzene, they align itself to form 4 sets of orbitals. These are particularly A2U, which is the bonding orbital having no nodes, followed by E1G. There are two doubly degenerate 2 sets of orbitals having one nodal plane. Then comes E2U, which is again doubly degenerate set of 2 orbitals having 2 nodal planes, and lastly it comes to B2G, which is antibonding orbital having 3 nodal planes. Now, these orbital the stack up in 4 sets of orbital in energetically, and the division is 1:2:2:1. And now it is important to construct molecular orbital in Biscarene complex using these 4 sets of energetically different molecular orbital. Now, before we do that, let us sort of see how these 6 orbitals A2G, E1G, E2U and B2G sort of align themselves to interact with various possible metal orbitals. So, we start off with the sigma interaction, which is shown over here. For example, for the A1G orbital, this is in these arene metal complexes where we have 2 benzene rings of 6p orbitals each. So, A1G combination is something like this. So, this is A1G and it can interact. So, A1G ligand orbital and the following metal orbital that it can interact with are S, and dz square. Similarly, the other combination would be A2U, where they would just flip over . . 。  . 。 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . to give a combination of something like this. So, in this alignment the dark shades are on the bottom and the top of the ring, but in this alignment A to U the dark shades are both at the bottom of the ring, and the corresponding metal orbital that would be interacting with it would be Pz. The interesting thing about these interactions are that all of these interactions are sigma type interaction, where like the electron density is maximum at the interacting internuclear axis. Okay. So, these E1G orbital of benzene in Biscarene complex would thus interact in a sigma fashion with S and dz square, and whereas A to U would interact in a sigma fashion with Pz orbital. Now, let us take a look at orbitals which would be interacting in a pi fashion, and these are E1G for the ligand. So, I am going to show it over here. The corresponding orbitals over here would thus be and the metal orbital would be d x z. The other combination is E1U. So, this is the metal orbital. The other ligand orbital combination would be E1U, which would again have the following combinations of orbitals in this case it is and the orbital which of the metal would be p x. Similarly, for the other E1g orbital, the combinations are which is of this combination and the metal orbital involves are accordingly d y z, and similarly the combination over here would be something like this. And the corresponding metal orbital would be a p y. Now, these 4 sets of orbital, this is of Gerardi symmetry and this is flipped over here, Ungerati symmetry. This also is of Gerardi symmetry, that flipped over here is Ungerati symmetry. So, they would combine with d y z, d x z, p y and p x, and all of these reflects pi type interaction. All of these reflects pi type interaction with the ligand interaction with the metal. So, now the last set of orbitals that involve in delta type interactions are shown over here. So, here this involves E2g orbital of this combination that would be interacting with d x y, and the other that involves is this combination and this dx square minus y square, and these orbitals are involved in delta type of interaction. So, we had seen that how these 6 orbitals, benzene orbitals, combine with the metal orbitals, resulting in 3 kinds of interaction: sigma, pi, and delta types, and the corresponding ligand orbitals which are involved in such interaction is shown over here. So, now we are going to move on to the most important aspect of it, which involves this construction of the molecular orbital correlation diagram, and this is done for the eclipsed conformation of bis-benzene chromium complex. As an example of case study, the symmetry is D6H, and we are going to construct this molecular orbital. Now, as far as the bis-benzene is concerned, in the eclipsed conformation, its ligand orbitals are A1G and A2U. Similarly, E1G and E1U. This will be E2G and E2U, and finally B2G and B1U. So, each 6 is having a 12 set of orbital 2, 4, 6, 8, 10, 12 of Gerardi and Ungerardi symmetry. Similarly, as far as the chromium is concerned, there are 5 d orbitals, these are d orbitals, and they are of A1G, E1G and E2G symmetry. Then there is one s orbital which is A1G, and then there are 3 p orbital, and this is A2U and E1U symmetry. Now, let us see how these orbital interacts with each other. For example, A2U is kind of non-bonding in nature, and remains by itself. This is A2U. Okay. Now, A1G interacts with A1G of the metal, which is A1G S of the metal, giving a bonding A1G orbital. And over here A1G star orbitals. So, the correlation diagram is somewhat over here. So, this A1G now is occupied. As a result, the A1G of the symmetry of the metal orbital remains non-bonding, G remains non-bonding. All the non-bonding orbitals are shown in green, and E1G interacts with E1G of d orbitals, E1G of d orbitals, and then correspondingly it is E1G star somewhere over here, and that is E1G star, and E1U of the benzene interacts with E1U of the p orbital, E1U, and the corresponding E1U of the p orbital U star 1U, and that is shown over here. E1U. So, this is now fully engaged, one with this, one with this, this one is also engaged, one is non-bonding. Now, we come to this E2U is a non-bonding orbital, E2U is a non-bonding orbital, and E2G interacts with E2G of this, so that is shown over here. E2G and E2G interacts, giving E2G star, and as a result, so one of these is non-bonding, the other one interacts over here. Similarly, for this E2 E1G is interacting, and A2U is a non-bonding. Somewhere here A2U, that is a non-bonding orbital, which is somewhere here, and these orbitals B2G and B1G remains unaffected. So, what sort of comes out over here, that between the 2AG combination, one is non-bonding in nature, whereas between B2U both are engaged and one is non-bonding for this, and similarly for the p orbital, one remains non-bonding. Now, this is done in a qualitative way. The most quantitative picture obviously is given in the screen. It is important that one sort of constructs this molecular orbital just to get a feel for all the bonding and the non-bonding orbitals and how they interact. So, with this I would come to the conclusion of today's lecture, where we have seen the construction of the molecular orbital for Biscarene complexes, how they interact and which remains bonding, antibonding and non-bonding, and that sort of explains the electronic structure of these compounds. So, with this I conclude today's lecture, and we are going to be taking up the structure and bonding in bit more detail, and followed by the reactivity of Biscarene complexes in the next class. Till then, goodbye and thank you.